today's session. So we will be starting, we'll be continuing ahead with center of mass system of particles chapter today. So in the last lecture, we looked at some examples of conservation of linear momentum for a system wherein the net external force being zero. The center of mass was either at rest or it could be moving with uniform velocity because the linear momentum was conserved. And that in turn happened because the net external force on such a system would be zero. Now, today's lecture will focus on a very important application of this concept of conservation of linear momentum, and that is in the situation where there are collisions happening between different bodies or different particles. So let's start the session. So this session is going to be very important in terms of the type of questions we deal with in this section later. Okay, and the weightage of these questions in JEE is going to be pretty huge. As I told you before, conservation of linear momentum is one of the major important concepts in mechanics as a whole. Okay, and mechanics has significant weightage in physics, as you know. So this is system of particles, session number 8. So we will look at the application of conservation of linear momentum in collisions today. So a collision is an event where in which a moving body or particle collides with another moving or stationary, both cases being valid, body, and as a result exchanges momentum. So there's a redistribution of momentum between the two colliding objects. Okay. So a good example of collision in everyday life is various sorts of board games that you play, like carom or snooker or billiards, etc. Okay, those are examples of collisions that you see in typical everyday situations. Okay, like you can have a carom coin like this, and you can have the striker which is struck at it like this. And as this comes and collides with it, okay, after the collision, what might happen is that the striker might go off in a direction like this, and the body it has collided it with might go off in a direction like this. Okay, whereas the original direction in which the striker was moving was this. Okay. So what happens in this type of a collision? So collision in a game of carom. So what happens in this is that initially an object approaches another object with a velocity vector like this, let's say, and the second object is at rest. So in the game of carom, these are disc-shaped objects. Okay. It might so happen that the velocity vector is not aimed at the center of this. So in such a case, what will happen after a bit of time is when they collide, the situation between them will look like this now. When they come in contact, the situation will look like this, whereas this one's velocity vector was along this sort of a line. Just a moment. Just have to share the screen again. Yeah. So this one's velocity vector would have been along this sort of a line. But when they come in contact, there is force acting between them. There's contact force acting between them. So what will happen is that as they come in contact, this one will be pushing that one with what we call a collision impulse force, which will act along this center to center line. And that one will be applying an equal and opposite collision impulse. And those forces will be along the center to center line. So it's like this is a force acting for a very short duration of time. So you can see that the net external force is 0 on the system. And as a result of that, the momentum of the system remains conserved. But individually, they start moving off like this. This will have a velocity vector along this sort of direction. Let's say V2. And this will have a velocity vector which is now, originally its velocity was in this direction, but a force acted on it in this sort of direction along the center to center line. Okay, so its change in momentum will be such that the initial momentum is along this line. The force acted along this line. So the final momentum might become along this sort of a line. So it might go off in this sort of a direction. Okay. Whereas this might go off in this sort of a direction. So this is an example of what we call an oblique collision. Okay. This is an example of because it's hitting it obliquely. And here the quantity J is impulse. It is in fact the collision impulse. Okay. We'll talk more in detail about impulse in a bit. Okay. So impulse is equal to force into time, where F is the average collision force, okay, that acts during impact. During the impact between the two bodies. And delta T is the time for which the bodies are in contact. During the impact. Okay. So anyhow, you can just make a brief note of this part. Then we'll look at more examples of collisions. Okay. Now another example of a collision. So I'll come back to the concept of impulse in just a moment. But another example of a collision could be something which is much more
Sir,
straightforward.
can you follow?
Ajay, you haven't finished writing? Okay, just a minute.
Sir, done.
Yeah. Okay, now another example of a collision would be where you have the same two objects, okay, but you are hitting what is called a direct shot. Okay, it's not an oblique shot. So those of you might have been, might be experts in carom will know very well what I'm talking about. But even others who might not be so passionate about carom, you will still get an intuitive idea when you look at the diagram here. So instead of aiming the velocity vector such that the vector does not pass through the center of this one. Okay. So this is our center to center line from this point to this point. But if the velocity vector of the first one, it is in such a direction that it's aimed directly towards the center of the second point or the second disk. It's aimed directly along this center to center line. Okay, and whereas the second one is at rest initially. Okay. So what will happen now this time when they collide is that the collision will occur in such a way that the direction of the collision force is exactly the same as the direction of the initial velocity. So the final velocity will also be along that same line. So you must realize that this is the top view of that carom table. This is the top view of a carom board. Okay. So this time when we aim it such that the velocity vector was already along this center to center line. It was not along some oblique line. Then this is called a direct, or in more technical language, we will now call it a head-on. It is a head-on impact instead of being an oblique collision. So why it is a head-on impact is because now the forces that act or the impulses that act, that is force multiplied by time. So they'll be along this same axis along which the initial velocity vector was. So now depending on how hard we hit it, right, and also depending on like whether the second one is a heavier or a lighter object, whatever be the case, these are equal and opposite. But as a result of this impact, now what will happen is that something like this might occur, that you will see that as they separate, okay, typically, especially if I assume that the first object, the blue colored disk over here, is lighter, then what we might expect is that it will recoil back, but the direction of its velocity will be along the same axis. It's not at some angle. It's at 180 degrees. It's along the same axis. So that is a head-on impact. Okay. Or it might even happen. So it might be like this. Okay. Or it might also happen so that they move in such a way that this one continues in this direction only. but it just slows down. This can also happen. That it doesn't recoil, it continues in the same direction in which that V naught was initially. So one of these two things is going to happen. Okay. So what happens in a head-on collision is that the final velocities, that is V1 vector and V2 vector after impact, okay, are collinear. So you'll recall from vector algebra, collinear means along the same line. Okay. And also collinear with the collision impulse or force, okay, J or F delta T. I mean J or F. So you can see these are all lying along this axis. Whereas just going back for a moment to the case of the oblique collision. Okay. So this is an example of oblique collision. Why? Because you can see that the final velocity vectors, they're not along a common axis. So what happens in an oblique collision is that the final velocities V1 and V2 are non-collinear. That is not along a common axis. They diverge at some angle which is not equal to 180. Okay. So that's an oblique collision, whereas this is an example of a head-on collision. Okay. Another example of a head-on collision, while you're noting this down, you can note it down simultaneously, is like this, that we have a smooth surface on which we have kept a block kind of thing, okay, and another block kind of thing like this. And it could even so happen that they are approaching each other. This is moving with a velocity u1, this is moving with a velocity u2, and they come and collide with each other. So this is before impact. And what might happen after impact is that this goes off with a velocity v2 like this, and this recoils with a velocity v1 like this. Okay. Because during the impact, as they come in contact, as they're just about in contact over here, they'll be applying impulse on each other like this, equal and opposite impulse. Okay. So this is also an example of a head-on or direct collision. Collision can also be called an impact. Okay. Yeah, so just make a quick note of this. We'll discuss further.
Sir,
Yes, tell me better.
sir, that circle comes back in this case. Now, when it will go with that big circle?
So it all actually depends on the amount of impulse versus the initial momentum. If the initial mass of, if the mass of this object is, let's say, m1, okay, and the mass of the second object is m2. Now, typically, if m1 is less than m2, typically I'm saying, not always, but if m1 is less than m2, then it will tend to come back. It will tend to recoil. That's the first diagram. Whereas if m1 is heavier than m2, then it will be the second diagram typically. Now you might say, okay, if it's a smaller object, how can it be heavier? But that's always possible. They might be made of different materials, right?
Yes, sir, understood.
It also depends. So while I said that typically, why I said typically, because also it depends on the nature of the materials. Like for example, if you have two stone objects which are colliding, you might get one kind of result. But if you have two objects like rubber discs or tennis balls or things like that, which have more elasticity, then you'll get a different kind of result. So it doesn't depend only on the masses m1 and m2, but it also depends on what materials these two bodies are made for. So collisions are affected by all these factors. Right. Similarly, even in the example of the blocks, it might be this way, or it might even happen that the first block continues in the same direction, but with a lower speed. V1 is less than U1. It continues in the same direction. And after impact, this one recoils. V2 becomes like this. That's also possible. So there are various different possibilities. It all depends on two things, the ratio of the masses and also the materials that the two colliding objects are made with. Okay. So before we take a further look ahead at collisions, we will first look at the concept of impulse a little bit. Okay.
Sir.
Impulse, yes.
Sir, so in Carom's case, the striker doesn't come back because its mass is more.
Yes, its mass is more, and also the carom coins and the striker are made with materials which don't have too much elasticity. They're not made of rubber or something like that, no?
Yes, sir.
But in the case of snooker or billiards, if you played those games, then the balls are all of same mass, no? So it is possible to get the ball that you are hitting with the cue. It's possible to get it to recoil. If you hit it in a certain way, it's possible to get it to recoil. So let's understand this first. Okay. So going back to Newton's second law for a particle. For a body or particle of mass m, it was that the net external force or the net force acting on it is rate of change of momentum. This is the definition of Newton's second law, where the linear momentum is mass into velocity. So if we cross multiply the dt then over here, then F net into dt is equal to dp. Okay. So this F net into dt over here, it is called the impulse due to this net force in the time interval dt. Okay. And this dp is the change in momentum in the time interval dt, during the time interval dt. So we say that impulse is equal to change in momentum for that small time interval dt. Okay. So now if we integrate both sides of the equation, we will get F net integrated from t equal to 0 to some time, let's say t. On the other side, we'll get the change in momentum from whatever initial momentum to whatever final momentum. So this quantity is called impulse. This is impulse due to the force, or in this case, that due to the net force from time t equal to 0 to t equal to t. Okay, so that net impulse is equal to final momentum minus initial momentum. So therefore, we can further say that the impulse, in fact, we'll call this the net impulse, because it is the net impulse due to the net force. Okay. So net impulse is equal to change in linear momentum. So this is called the impulse momentum theorem for a single particle. Okay, this is called the impulse momentum theorem. Okay. So the statement of this theorem is that the net impulse on a particle or body equals, but of course, when we are saying net impulse, it is during a certain time interval. So the net impulse on a particle or body during a certain time equals to the change in momentum during that time interval. Okay. So we'll talk a little bit more about this also. First, just note down this much part. So impulse is basically equal to force integrated over time. So net impulse equals to the net force integrated over time. Okay. So J is equal to F dt from T equal to T1 to T equal to T2. This is the general definition of impulse due to a force F. From a certain time T1 to a certain time T2.
Done, sir.
Okay, done. Okay, now one final thing about impulse before we come back to collisions is that if F is a constant force, that is both magnitude and direction are constant, then impulse due to that force, which is integration of F dt from T1 to T2, will simply become F into integration dt, or it will become F into T2 minus T1, or F delta T. So for a constant force, we don't need to use integration. Impulse J is equal to simply F delta T in a time interval of delta T. Whereas for a variable force, impulse will have to be defined by integration from whatever initial time to whatever final time. So it's a bit like work done. Work done by a constant force we define as dot product with displacement. But work done by a variable force has to be defined by the path integration, F dot ds integration. Okay, so now talking about a system. For a system of particles or system of mass, okay, we know that the net external force is equal to rate of change of momentum of the system. Okay. Where we also know that the momentum of the system is defined as total mass into velocity of center of mass, or it is sum of momenta of the individual particles of the system. So capital M is total mass. Okay. So now if we see, if we cross multiply the time on this side, we can see that again integration of the net external force from whatever time t1 to whatever time t2 is equal to the change in momentum for the system. So this is the way we express the impulse momentum theorem for a system of particles. So for a system of particles, the impulse due to the net external force in a certain time interval t equal to t1 to t2 equals to the system's change in momentum during the same time interval. Just make a quick note of this.
Sir, 1 minute.
Yeah.
Done.
Done now? Okay. So once again, if we focus on that part, that what happens for a system for which the net external force is 0. Okay. That means the impulse equals to 0. That means the momentum of the system is conserved. Okay, something that we know already, but that is now coming in the language of, because this is basically the net external impulse. That is equal to integration of the net external force into time, which is the change in momentum for the system. So if this only is 0, okay, because the net external force is 0, then the momentum is conserved. So collisions, any collision is an example of this situation. Which situation? That the net external force is 0. Okay. So net external impulse is 0. So momentum of the system, that is the momentum of the collided bodies, is conserved or constant. So whether we are talking about an oblique collision or a head-on collision, oblique or head-on, okay. Later we will learn the term elastic or inelastic. Okay. Elastic collision is a collision between bodies made of materials which have high amount of elasticity or which are elastic in nature, whereas inelastic collisions are collisions between bodies which have very poor amount of elasticity or basically are inelastic in nature. Oblique and head-on we've just understood, but whatever be the case, okay, any collision will be an example of the situation where the net external force is 0, which means the net external impulse is 0, which means that the momentum of the system is conserved. That is the total momentum of the colliding bodies that is conserved.
Sir.
Yes.
Sir, in the red brackets you have written oblique or head-on, elastic or inelastic, because I'm not able to read it.
Yeah, I mean, by any collision, I mean that these are different categories of collisions. Okay, oblique or head-on, they are two different categories. Similarly, we will study very soon that elastic versus inelastic. These are also two different categories of collisions. Okay, when we call the collision elastic, when the material of the bodies which are colliding are highly elastic in nature, like two tennis balls colliding with each other, or like two of those funny rubber balls that collide with each other, made of soft rubber. So they are highly elastic in nature. Whereas inelastic collisions are collisions between bodies made of materials which don't have much elasticity, like like a heavy iron block colliding with a piece of stone or a brick or something. So these type of materials are not very elastic. Is it clear now?
So you mean materials which are elastic, that is, they can easily deform and they can again restore its shape?
Yes, yes.
So you have
Materials
written
which have that oblique or head-on.
Okay, or
Head-on. Oh, sorry, it should not be off, it should be or. So whether it is oblique or it is head-on, whether it is elastic or it is inelastic, whatever be the case, as long as we are talking about a collision between two bodies or a collision situation, the momentum will always be conserved. Any type of collision, this or this or this,
Sir,
momentum
but if
conservation is a
external,
universal fact. Yeah.
Sir, if external force is zero, then only, no, but
Because in a collision, always external force will be zero. No? It is the only force that acts between the bodies is the mutual force that acts on the impact. No? That's an internal force.
sir, so for collision, external force is zero.
Yes. A collision, see what we have defined the collision as. It is an impact between a moving body and another body which is either at rest or moving. No? So there is no external agent involved in a collision.
Yes, sir.
You understand the way we have defined the situation of collision? No? See, if suppose when the two objects are impacting each other, an external agent is pushing one of the objects, then of course external force will not be zero. But then that is not coming in our category of collision. No? What type of event we are taking as a collision? Very simple event where a moving body simply hits or impacts another body which is moving or which is at rest. So that situation itself dictates that there is no external agent involved. Okay. Simple, understood this point of time?
Yes.
Just visualize the two or three examples we saw above. No? The carom coins colliding on the surface of the carom board, or one block moving towards another block which is coming towards it, two blocks approaching each other. When they are colliding, now at the time of impact, there is no third external agent which is applying any force on the system. No? The only forces which are acting are the mutual impact forces or the mutual impact impulses because of those forces. So external force or external impulse is zero. So momentum conservation is a universal fact for this kind of events, which are called collisions. Okay. So now we will understand the different types of collisions one by category. So the first category of collisions that we'll study are the head-on collisions. Okay. We'll study them by different categories. Okay. Or properties. So the first category of collision that we'll study about is the head-on collisions. Okay. Or these are also called one-dimensional collisions. It's very easy to understand why they are called one-dimensional collisions, because all the vectors, the initial velocity vectors, the final velocity vectors, they lie along one axis. So the system is one-dimensional. So in short, we will just call them 1D collisions from now. So the generic basic model that we'll have of this is, let's say we have a particle of mass m1, which is moving with a velocity vector v1, or rather u1, along the positive x-axis. Okay. Now that goes and hits another particle, which is also, by the way, in motion and moving along the same axis, but with a velocity u2. So my sign convention is such that when u1 and u2 are positive, they should be moving along the positive x-axis. And this one has a mass m2. So if u1 is greater than u2, that means particle m1 is approaching. It is approaching the second particle m2. Okay. In fact, it has an approach velocity. You would have heard the term approach velocity in kinematics, right? Is the relative velocity along the center to center line. So the approach velocity will become how much? u1 minus u2. This is the relative velocity of approach. It is the rate at which the distance between them is decreasing. So as long as u1 is greater than u2, this is what is happening. They are approaching each other. Okay. So after a bit of time, when they come in contact, now also as vectors, u1 and u2 are collinear. They lie along one axis. Okay. And are along what we call the line of impact. So what is the line of impact? It is the line along which the mutual collision force or the collision impulse will act. So when they come in contact, this is before contact or before impact. Or when they come in impact, during the process of impact, this is what is happening. They have come in contact, so they will be applying some kind of force on each other. And that will be an equal and opposite force. The force that particle 1 applies on particle 2 will be like this, and the equal and opposite force that 2 applies on 1 will be like this. So we can even, in a proper language, we can show that this is the force that 2 experiences because of 1, and this is the equal and opposite force that 1 experiences because of 2 while they are in contact. Okay. So the line along which these forces act, this is called the line of impact, and that is collinear with the initial velocities u1 and u2. You can see. So this is called the line of impact. Okay. So here F21 is equal to minus of F12. This is the collision force applied by M1 on M2. And similarly, this is the collision force applied by M2 on M1. So they are an action-reaction pair. They are an action-reaction pair. And that is why you can see that, therefore, for the system that is M1 plus M2, the external force is 0, because these two forces cancel in action-reaction pairs. So U1 and U2 are collinear and are along the line of impact. What is the line of impact? The line along which the impact forces act. Okay. So after collision, let us say the situation becomes now like this. So in our diagram over here, which is the generic diagram, we will assume that both continue in the same direction. But what happens? This one, its velocity increases because impulse is acted along its original momentum. And this one, its velocity decreases in magnitude because impulse is acted in the opposite direction. So we'll assume that this one develops a velocity v1, which is less than this u1, and this one develops a velocity v2, which is greater than u. So this is after impact. Okay. And what will happen after impact is that v2 will become greater than v1. So m2 is separating away from, or it is moving away from, or its distance is increasing with respect to m1. So we have the velocity of separation. The relative velocity of separation will become equal to v2 minus v1. Okay, so this is the general situation of this head-on type of collision or one-dimensional collision. So just make a note of this first, then we will apply the momentum conservation principle here because the net external force is 0. Let's see what we'll get next when we apply the momentum conservation equation.
Sir,
Yes.
sir, if U2 is greater than U1, then what?
Then the collision hoga hi nahi na, because
Ah,
then
yeah.
the distance between them is increasing. Okay, so for the collision to happen, this is the necessary condition. U1 must be greater than U2. This is necessary for collision. For impact to occur, this must happen. They must be approaching each other. They cannot be separating before. Okay, so now the first equation that we can see, we can write over here. So by conservation of linear momentum, how we can write conservation of linear momentum? Because the net external force is zero. We've seen that before. So what should happen is that m1u1 plus m2u2 vector sum should be equal to m1v1 plus m2v2. But that will over here imply that m1u1 plus m2u2 scalar sum only is equal to m1v1 plus m2v2 because it is one dimensional. Okay. So this becomes our equation 1. Okay. Now we come to an interesting fact. Okay. Now, if the two particles are made of elastic materials, example, soft rubber, okay, such that the kinetic energy of the system does not dissipate, that is, remains conserved. Okay. Then such a collision is called, so this is an important definition, it's called a perfectly elastic collision. So what is a perfectly elastic collision? Where there is no loss of kinetic energy. Because there's no dissipation of kinetic energy to any other form of energy. So, you know, two particles or two small objects made of soft rubber, when they collide, you will not be hearing any sound. They will not get dented in any way. You will not be hearing any, there won't be any sparking, etc. So that means the kinetic energy is not dissipated to any other form of energy. Whereas, you know, if you take, let's say, two wooden blocks that collide with each other, so there will be a sound that you will hear. Where the collision occurs, the wood might get dented, it might get disshaped. So that means that there is some kind of molecular bond energy that is breaking, you know, because the intermolecular bonds are disturbed. So kinetic energy is getting converted into other form of energy because it's breaking into the bond energy, etc. But in the case of elastic materials, where there is no evidence of this kind of thing happening, that neither they're changing shape in any way or they're getting deformed in any way, nor you're hearing a loud sound or a sparking or anything like that. So that means the kinetic energy of the system is remaining conserved. So such a situation where there is zero loss of kinetic energy, it is called a perfectly elastic collision. So that is the definition of perfectly elastic collision. There is zero loss or dissipation of kinetic energy. So if we apply this case to the above problem now, then we are dealing with what is called the perfectly elastic head-on collision. Because on the one hand, in terms of geometry, the collision is one dimensional. And on the other hand, in terms of materials, it is perfectly elastic because we are assuming that there is no loss of kinetic energy. So that becomes the first, you can say, subcategory of head-on collision, which is the perfectly elastic head-on collision. So in this case, the collision will then be called, so this case of head-on collisions when there is zero loss of kinetic energy is the perfectly elastic head-on collision. or perfectly elastic one-dimensional collision when there is zero loss of kinetic energy. So now for this case, we will get a second equation along with the momentum conservation, which was the first equation. We will also apply the conservation of kinetic energy. Okay, so along with conservation of linear momentum, for the case of perfectly elastic collision, we have the conservation of kinetic energy, which will result in the equation that half m1 u1 square plus half m2 u2 square, which was the initial kinetic energy of the system, will become half m1 v1 square plus half m2 v2 square after the impact. So this is the second equation after the linear momentum conservation. So given m1 is known to us, m2 is known to us, u1 is known to us, u2 is known to us, we can find the final velocities for a perfectly elastic head-on collision
Sir,
by solving. Yeah,
so this conservation of momentum and kinetic energy is applicable for every collision.
conservation of momentum is applicable for every collision, but conservation of kinetic energy is applicable only for the perfectly elastic collisions. When there is inelastic collision, then there will be loss of kinetic energy.
Okay, sir.
Understood? So conservation of momentum is a universal fact for all types of collisions. In fact, not only for head-on collisions, it's true for the oblique collisions also. Whereas conservation of kinetic energy is a universal fact for which type of collisions? Perfectly elastic collisions, not for the inelastic collisions.
Sir,
Yes.
so sir, in that second equation, did you multiply LHS and RHS with half?
Sorry, in the second equation, did we?
Multiply that first equation both the sides with half. That 1 minute.
No, second equation is kinetic energy, na beta. So kinetic
Okay,
energy
okay.
का तो definition ही half mv square होता है ना,
Ah, sir, getting it.
है ना? So the total kinetic energy of both the particles before impact, that is the left hand side, and the total kinetic energy after impact, that's the right hand side. And why we can equate them? Because there is zero loss of kinetic energy, because they are made of elastic materials.
Yes, sir, as far as definition is concerned.
Yes, okay. So now you can see that given this kind of situation, that suppose we are given numerical values of m1, m2 and u1 and u2, then we need two equations to solve for v1 and v2, and we have these two equations. But the solving, we have to develop a method, a systematic method, because it's not like two normal simultaneous equations. You can see the first equation has terms v1 and v2. The second equation has terms v1 square and v2 square. So we have to develop a system to, a sort of systematic method for solving the two equations. So for that, we have this method below. Okay, so that gives us some useful information also. So note that for solving equation 1 and 2, we manipulate them in this way, that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. We can write it like this now, that m1 multiplied with u1 minus v1 is equal to m2 multiplied with v2 minus u2. I will understand in a moment why I am manipulated like this. I've taken the terms of subscript 1 on one side and subscript 2 on the other side. Okay. Then similarly, so this was the first equation. Similarly, the second equation was half m1 v1 square plus half m2, sorry, m1 u1 square plus half m2 u2 square. The initial kinetic energy is equal to the final kinetic energy.
Sir, I have to write that last part.
Okay, I'll take you back to that. Okay. Now, in this, what we can do is we can first of all cancel the halves on both the sides and again use that same trick of taking m1 on one side. So we have u1 square minus v1 square, and taking m2 on the other side, we have v2 square minus u2 square. So now what we can do with this new form of equation 1 and 2 is that we can divide them. So that will give us an interesting equation. We take equation 2 and divide it by equation 1. So we have u1 square minus v1 square upon u1 minus v1 is equal to, on the other side, v2 square minus u2 square, again divided by v2 minus u2. And then further manipulating algebraically, you can see that we'll get the relation that u1 plus v1 is equal to u2 plus v2, which will give us further this interesting fact that u1 minus u2 is equal to v2 minus v1. Now, if you recall, this is something significant. This was the approach velocity. This is the relative velocity of approach. Okay. In the diagram, we had understood why that's the case. And this is equal to the separation velocity. So that means there is an additional property that goes with the perfectly elastic collision. Whenever the collision is perfectly elastic, not only the kinetic energy is conserved, but also what happens is that the relative velocity of approach equals to the relative velocity of separation. Okay. And after impact, this was running away faster with v2. This was chasing it with a slower velocity v1. Okay. So this is after impact. This was before impact. So you can see from the diagram that our approach velocity before impact, it was u2 minus u1, and our separation velocity after impact, it became v2 minus v1. And now this conservation of kinetic energy along with conservation of linear momentum is showing us that this is what happens. So this is an additional property and an important property of elastic collisions. So therefore, in a perfectly elastic collision, okay, kinetic energy is conserved, but along with that, what else happens? And separation velocity is equal to approach velocity. Okay. The relative velocity of separation after impact is equal to the relative velocity of approach before impact. Okay. And now you can see that if we use this as a sort of third equation, then we can always solve for v1 and v2 using equations 1 and 3 instead of equations 1 and 2, because they are simple simultaneous equations. So they are much easier. Okay. All right. So I'll just take you back to the previous section once. Okay. And then we'll come back to this. But basically, the previous section only results in this section that we are applying the conservation of kinetic energy along with the conservation of linear momentum. So when we solve these two equations, conservation of linear momentum giving us equation 1 and conservation of kinetic energy giving us equation 2. When we solve them when we solve them using this method that we've done here, that we divide equation 2 by equation 1, but after first manipulating them in this way, you see that we get the interesting property that kinetic energy conservation also means that the separation velocity should be equal to the approach velocity. Because there is no loss in kinetic energy, that's why what happens is that the rate at which they are moving away from each other after impact is exactly equal to the rate at which they are moving towards each other before impact. In fact, we will see, as you might have guessed, that if there is loss in kinetic energy, like in the case of inelastic collisions, then the separation velocity will in fact become less than the approach velocity. Separation velocity cannot be more than the approach velocity. It will either be less in the case of inelastic collision, or it will be equal to in the case of perfectly elastic collision.
Sir,
Yes.
sir, so
Yes.
U1 is the initial velocity of mass M1 and V1 is
Yes.
final velocity.
And v1 is the final velocity. Okay, that you've seen in the diagram before only. No? You've seen that before impact, this diagram. No? Before impact, u1 and u2 were the velocities. Okay, and after impact, v1 and v2 are the velocities.
Sir,
Yes.
sir, could you just scroll down?
Yes. Okay, done with this, people?
So just last line left.
Sir,
Okay.
sir,
Yes.
sir, can you explain that separation at once?
हाँ, because देखो यहाँ पे by dividing the two
Sir, here
equations,
not.
like,
Sir, that you have told now V2 greater than V1.
So separation velocity क्या होता है? It is the relative velocity at which two objects are moving away from each other, na? So if like you have a particle which is moving at 5 meters per second like this, and it's being chased by another particle which is moving only at 2 meters per second, then what is the rate at which the distance between them is increasing? It's 3 meters per second, na? So here they are separating from each other. So B is separating from A with how much relative velocity? 3 meters per second. So if this is your V2 and this is your V1, then obviously that's equal to V2 minus V1. This is clear now?
Yes, sir.
Okay. Whereas if the same thing, the two particles were moving towards each other because A had the higher velocity. Suppose A had a velocity of U1 equal to 4 meters per second, whereas B was moving away at, let us say, U2, which was 3 meters per second. Then instead of separating, they are approaching each other. The distance between them is decreasing. So in this case now, the approach velocity of A towards the particle B, that's becoming how much? It's becoming 1 meter per second. So that is your U1 minus U2. This is just an example I'm giving you, but in general it is U1 minus U2, and in general the separation velocity after impact becomes V2 minus V1. Okay, so clear?
Yes, sir.
Okay, now let's see how we can apply this in actual numerical problems. Okay, so for example, we have this situation now. Let's take the simplest possible case that one of the two objects is in fact at rest. Okay. So the second one is not even moving, it is at rest. This is a frictionless surface, whereas A is moving at a velocity V0. Okay. So mass of A is suppose equal to 4 kilograms and mass of B is equal to 2 kgs. Now A moves at V0 equal to, let's say, 16 centimeters per second on a smooth surface, okay, to make a perfectly elastic head-on collision with the stationary object B. So we want to find the velocities of A and B after impact. Okay. And the collision impulse by A on B or B on A. How much impulse they apply on each other as a result of the impact. So what we can do here is we can just reduce this to this kind of a situation. We can convert it to M1 is basically the particle A, which is moving at U1, okay, which is going to be that speed V0. And M2 is the mass of the particle B, which is at U2 equal to 0. It's at rest. Okay. And the collision is perfectly elastic. So after impact, whatever velocity the particle A will have, that we'll call as V1. And after impact, whatever velocity the particle B will have, we'll call that as V2. Okay. So we have the formula that conservation of linear momentum So that is M1U1 plus M2U2 is equal to M1V1 plus M2V2. So in this case, that will become mass of A into V0 plus 0 is equal to mass of A into V1 plus mass of B into V2. So let's substitute the values. So 4V0 is equal to 4V1 plus 2V2. So this is what we are getting numerically. In fact, we can divide by 2 also. So this is what we are getting numerically from the conservation of linear momentum. Then we have the fact that the collision is perfectly elastic. Okay. So perfectly elastic means two things. One is kinetic energy is conserved, but that's a very complicated equation, as you can see. The other also means that separation velocity should be equal to approach velocity. Now this is an even easier equation to use because it's a linear equation. So separation velocity kitna hota hai? V2 minus V1, that should be equal to approach velocity, which is U1 minus U2. So in this particular case, that separation velocity V2 minus V1 should be equal to approach velocity, which will be U0 or whatever V0. It should be V0 and this one is 0. So we have the relation that V2 minus V1 is V0, which was how much? I had given it as 16 centimeters per second. So now we can see these equations are very easy to solve. Okay, equation 1 and 2, they're very easy to solve. So now solving 1 and 2. In fact, equation 1 can be written as 2V1 plus V2 is equal to 2V0. Okay, or 2V1 plus V2 is equal to 2 into 16, 32 centimeters per second. And equation 2 is V2 minus V1 is equal to 16 centimeters per second. So you can see if you just subtract these two equations, you will get rid of V2 and you will get 3V1 is equal to 32 minus 16, that is 16. So V1 is equal to 16 by 3 or 5.33 centimeters per second. And V2 will therefore become equal to 16 plus V1 from equation 2. So it will become 21.33 centimeters per second. These are the values we are getting. So what that is showing us that V1 is a positive quantity plus 5.33. So that's showing that even after impact, the block A will continue moving in the same direction, but with now a speed of only 5.33 centimeters per second. Whereas the block B was at rest initially, now it will have a velocity of V2, which is 21.33 centimeters per second. This is what is happening after impact now. Whereas before impact, this one was approaching this at a velocity of 16 centimeters per second, and this one was at rest. So they collided, and as a result of the collision, now this one has slowed down from 16 to 15.33, and this one has sped up from 0 to V2 equal to 21.33. In the process, you can see that momentum is conserved. If you do the calculation of momentum, you will see that it's conserved because 4 kg into 16 will give you 4 kg into 5.33 plus 2 kg into 21.33. It will give you that value. And also you can see that the approach velocity in this diagram, you can see that the approach velocity is 16 because this one is at rest. And in this diagram, you can see that the separation velocity is 21.33 minus 5.33. So that's also equal to 16. So you can see that the approach velocity is equal to the separation velocity, which is what should be the case because it's a perfectly elastic collision. So this is the general method of solving a problem like this numerically. Now, we use the predetermined concept that we have developed already about the head-on perfectly elastic collision, that the two equations we'll be using to solve numerically. One of them will be the conservation of linear momentum, and the other will be the fact that approach velocity equals to the separation velocity during the impact. I mean, during the elastic impact, perfectly elastic impact. So we got the results over here only. Just note them down. Then I've just explained it over here, what it means therefore finally.
Sir, sir.
Okay, people, so hope this example is clear with the application. So let's solve a couple of more questions.
Sir,
Yes.
sir, could you just show the last part? Actually, you didn't show that part.
Yeah. Okay, so take it down and now solve the next question yourself. The next example, we'll see something interesting. Let's make the first object the lighter one, and the second object which it's colliding with, that's the heavier one. Let's see what happens in this case. This one is moving at a speed of, let's say, 6 meters per second on a smooth surface towards the second object which is at rest. Now mass of B is equal to, let us say, 3 times mass of A. Okay. And the collision is a perfectly elastic head-on one. So find the final velocities. So before we come to this, there's a second part in this earlier question to solve for the impulse. The second part, the impulse on impact. So we have to see that, this one coming at a speed of v naught comes and hits this one which was at rest. Now, as they come in contact, they're in contact for a short duration of time. So they apply force. Okay, so integration of force over that time delta t, that is the collision impulse. Impulse due to collision. Okay, where delta t is the duration of the collision. It is a short time for which they are in contact. And F is the collision force or the impact force. So how we'll calculate this? So we will see that after the impact, what is happening? B has developed a velocity of v2 and A has reduced in velocity to v1. So for B, we can see impulse equals to change in momentum. So we can see that the impulse is in the positive x direction and the change in momentum is also in the positive x direction. It is plus m2 v2 minus 0. Initial momentum was 0. So you can see that the collisional impulse will have become mass of B was 2 kg and into this velocity was 21.33 centimeters per second. So it is 42.66 kilograms centimeters per second. Okay. Now you'll see that if you apply the same theorem on A, you will get the same magnitude of impulse. But on A, you have to understand that the direction of impulse is opposite. So if you apply the same theorem, impulse momentum theorem for the particle A now, you will see that the impulse acts in which direction? It acts in the negative direction. So that should be equal to the change in momentum. So the final momentum is ma into v1. The initial momentum was ma into v0. So you'll get that minus j is equal to ma into v1 minus v0. Or therefore you can get j is equal to mass of A into v0 minus v1. Now, if you substitute the values, you will see you'll get the same magnitude of impulse because, of course, these and this are action-reaction pair. So mass of A was 4 kg and the initial moment velocity was 16, whereas the final was 5.33. So you will see that when you calculate this, you get the magnitude of the impulse as the same thing. Get it as 42.66 kilogram centimeter per second. Okay, so that's justifying your momentum conservation, because the impulse acting on A is positive of this much. Sorry, the impulse acting on B is positive of this much, and the impulse acting on A is negative of this much. So the net external impulse is zero. So no wonder the momentum is conserved. So during a collision, if we are asked to calculate the impulse due to the impact forces, this is how we calculate the impulse. We calculate it by using the impulse momentum theorem, that impulse equals to the change in momentum.
Sir,
Yes.
so sir, are you neglecting the friction?
Neglecting the friction in the sense that the surface we have assumed is frictionless. No? The floor is frictionless.
Okay, okay.
So friction is not playing any role over here. No? But even if there had been friction, what would have happened? Friction would not have played a role during the impact, because the time of impact delta t is very short. But yeah, before A comes and collides with B, it would have slowed down compared to the initial velocity, like that. But in this case, yes, we have taken a perfectly smooth floor. There is no friction involved.
Because sir,
Yeah.
because if in case if there had there been a friction, then the velocities would be variable before and after.
Yes. 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 Before and after would be very good. That's correct.
Sir, could you show the right part, left part as well?
Yeah. So the first question is done now for the left part.
Yes, sir. Done.
Yeah. Yeah. So let people just finish the second part of the first question, and then I'll come back to the second question which I've asked you to solve.
Sir, can you explain the second part, the downward part again?
So second part, what we are doing is we are applying the impulse momentum theorem, that impulse due to the collision force is equal to the change in momentum for each of the bodies. So if you look at the body B, just concentrate on the diagram of the object B. What's happening? Initially, it was at rest, and its final velocity is v2 in the positive x direction, right? So change in momentum uska kitna ho jayega? Final minus initial. So that's plus of m2 into v2.
Yes, sir.
Right. So left hand side, what is that change in momentum equal to? It's equal to the impulse. So the impulse should be equal to m2 into v2, and the direction of the impulse is also positive. Okay, so for B it's clear.
Yes, sir. Be clear.
Now for A we are applying the same thing. Impulse is equal to change in momentum. But remember, impulse and momentum are vector quantities. So here they are one-dimensional vectors. No? So their direction is shown with algebraic sign plus or minus. Instead of unit vectors, no, we are using the algebraic sign. Okay.
Yes, sir.
So A पे जो impulse लग रहा है उसका magnitude J है, but what about the direction? It's towards the left, no? So it should be written as minus J.
Yes, sir.
So that should be equal to the change in momentum. So that's final momentum minus initial momentum. So that will give you the same magnitude of J as you are getting for B. Why same? Because obviously their magnitudes have to be the same because they are action reaction pair.
Yes, sir.
Okay, so I'm sure this part is done now. So let's come to this next question. So now you have to just make a sort of repeat of the above solution, but the values are different. Now this time B is the heavier one, A is the lighter one, and B is heavier by a factor of 3. So just apply the equations like we've done in the previous question and calculate the final velocities of A and B. Yeah, anybody got the final velocities of A and B?
7 minutes we are doing.
Yeah, okay.
So can you show the right part?
Jay, check your solution again, but it's not correct.
Sir, can you show right part?
Okay.
Sir, you are muted.
Okay. Yeah. Now this is clear. In this diagram,
Yes,
I'll take M1 as A's mass and M2 is B's mass. So they're in 1:3 ratio. So इसको M लिख लो, इसको 3M लिख लो. And U1 is +6, but U2 is 0 because B is at rest. Okay. So now we have the relation that M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. So for this, we will get that M into 6 plus 0 is equal to MV1 plus 3MV2. Okay. So this is the first relation that we are getting, that V1 plus 3V2 is equal to 6. Okay. This equation all of you must have got.
Yes, sir.
Right. And the other thing is that separation velocity should be equal to approach velocity, because it's given to us that is perfectly elastic. Okay. So V2 minus V1 should be equal to U1 minus U2. I mean, you can write in any order. Approach is equal to separation or separation is equal to approach. Doesn't matter. So V2 minus V1 is equal to 6. Okay. So this is our separation. So same method. Now you compare the two equations. So V1 plus 3V2 is equal to 6, and V2 minus V1 is also equal to 6. Okay. So this time if we this the equations. Okay. Or you can also subtract the two equations. It doesn't matter, whatever you choose to do. So we get that. Sorry, if we add the two equations, it's easier. Yeah. So you'll get 4V2 is equal to 12. So that means our V2 is equal to plus 3. Okay. And not very surprisingly, we'll see that V1 will come out to be negative when we. So V1 is equal to V2 minus 6. So we'll get V1 as in fact minus 3 meters per second. So like I told you earlier, that in certain cases, if a heavier object collides with a lighter one, it tends to recoil. So this is what is happening over here. A block of mass m traveling at 6 meters per second collides with a heavier block of mass 3m. So after impact, what's happening? The lighter one is coming back at 3. The minus sign is showing us that. It shows that A recoils or it reverses its direction. That's what it shows. Okay. Whereas B will go in the forward direction, but with a velocity of 3 meters per second. So you can see that even after impact, they're separating at 3 plus 3, 6, because now they're going in opposite direction. So their relative velocity will not be 3 minus 3, there will be 3 plus 3, it's 6. Whereas before impact, the approach velocity was 6 minus 0. So approach velocity, you can see, was 6 minus 0, which is 6. And now you can see separation velocity is 3 minus of minus 3, or 3 plus 3, that's 6. And if you check out the momentum, that's also conserved, because 3m into 3, that's 9m. 9m minus 3m, that's 6m. And the initial momentum is also 6m. So the result is completely correct, because it's satisfying momentum conservation and approach velocity equal to separation velocity. Okay. So it's quite simple. Once you are familiar with the equations, you can see. Now, just like we have derived the equation for perfectly elastic head-on collision. So what are the equations? That momentum conservation is the first equation, and that separation velocity equals to the approach velocity. Now, similarly, we'll develop a systematic method for solving inelastic collisions, perfectly inelastic collisions, and all other categories of collisions. And then we'll move on from head-on collisions to oblique collisions, where we'll have to do the same kind of analysis, but in 2-dimensional vectors instead of 1-dimensional vectors. And with that, we will complete collisions chapter, or the section of collisions, which will complete system of particles. So that's it for today's session, people. For Sunday's DPT, just prepare up to the previous lecture, that is conservation of linear momentum examples. You don't have to prepare collisions in detail, okay, for that. So wish you all the best.
Thank you, sir. Bye, sir.
Okay, bye, people.
Bye, sir. Thank you, sir.
Okay, people, bye.